My name is Ernest Pokropek, and I'm really excited to showcase my research that I've been working on this summer in the Autumn Lab at the Robotics Institute of Carnegie Mellon University during the Robotics Institute Summer Scholarship Program. This is actually my second time at this, although first time here physically. This summer I've been working on the problem of blood loss prediction from non-invasively collected vital sign data under the mentorship of Dr. Nicholas G. Solfi, Professor Artur Dąbrowski, and with immense help from Rachel Lee, who are also listed here as part of our team. So as I mentioned previously, we want to estimate the amount of blood loss from non-invasively collected data. This will be extremely useful for trauma care, which is the focus of this project. That is, scenarios with traumatic injuries, dynamic environments, and no access to invasive collection methodologies, as well as no prior information about the patient. For this, we utilize the so-called withdrawal, dwell, and reinfuse cycles, basically an intervention into a dynamical system. It consists of withdrawing the blood for 20 seconds, then holding it for another 20, and finally reinfusing it also for 20 seconds. And simultaneously, we collect the vital sign data. The intuition is visualized on the right side of the slide, a system which in our case is a biological body, which reacts differently to external stimuli when it's healthy and where there's some problem involved. So a few words about the setup of our experiment. This is our prediction pipeline. So for this study, we have used data collected from 28 laboratory pigs, which were anesthetized during the procedure. After some time of stabilization, they were exposed to a constant bleeding rate of 10 milliliters per minute, resulting in maximal blood loss reaching almost 1.5 liters for some subjects. Both waveform and beat-to-beat measurements have been collected. Waveform in our case was ECG measurements, and the beat-to-beat were the plethysmography measurements. Data from WDR procedure has been used together with 10 seconds before and 20 seconds after the cycle, so we had like in total of 90 seconds time frame for each of the WDR cycles. And for each, we have computed windowed features, 42 of them to be specific, in 10-second windows with step size of 2 seconds. So then each window has an associated amount of bleeding to it, function as the predictive target. The feature-wise data has been later fed into the gradient boosting regressor in a leave one subject out cross-validation. The model has been trained on data from 27 subjects and tested just on one, and this has been of course repeated for every single subject. The predictions from one WDR cycle have been then aggregated by computing the mean, because remember we have plenty of predictions per one WDR cycle because of the windows, so we compute the mean of them, and this serves as a final prediction, so that later yields one value of bleeding predicted per WDR cycle. So here we have the accumulated results from all of the cross-validation folds, where the actual value of bleeding is presented in blue color, whereas the prediction in red. There's also a linear trend line fit to the predicted data to see how close it is to the original 10 milliliters per minute rate in black. We see that the model clearly picks up the trend and is able to predict the exact amount of blood loss with some degree of accuracy. Of course, there are some flaws of the current approach, and I want to address them in the next slide. So this approach is especially exciting given that we only need 90 seconds to establish the total blood loss of a patient, and we have no prior information about it, and we also use only non-invasively collected measurements. However, as the research is in early stage, we have fallen onto a problem of very different performance over different subjects. So here on the left side, you can see that whereas for the pig of index 13, which is in green, the pipeline performed extremely well, we cannot say the same thing for the pig of index 28, the red color on the plot. We expect that it is caused by the individuals being naturally different, and in the next stage of our work, we want to address the problem by exploiting the WDR cycles even more. We could have just used the data from the baseline to standardize it, but it kind of misses the point when we need to use half an hour of vital sign collection in order to use a 60-second WDR cycle to prediction. So thank you so much for your attention. I would like to take this opportunity to thank my mentors during the summer. That is Dr. Nicholas G. Solfi for accommodating me in the lab and always finding time for an extra brainstorming meeting throughout the week. Professor Artur Dąbrowski for extremely helpful suggestions and his time during our weekly meetings in the Autumn Lab with our interns, as well as helping me to accommodate in Pittsburgh. And of course, big thanks to my 2020 risk mentor, Rachel Lee, who has immensely helped me this summer with understanding and processing of medical data. So last but not least, I will also want to thank a lot Rachel Bochin and Dr. John Dolan for creating this opportunity and incredible management of the program throughout the summer, as well as individual help for every member of which cohort in need. So thank you all so much and wish you a great day.